The focus of the second half of Chapter 12 was to introduce you to the idea of a gradient and its uses in finding different things in multivariable calculus. So just to review, we have what's called the del operator, which is this upside down triangle thing. It is equal to d dx, d dy, d dz if we have three variables. And so therefore del f is equal to df dx, df dy, and df dz. And we use this to find our directional derivative, which is the derivative of a function in the direction of u, and it was equal to del f dot u, but u had to represent a direction, so you had to make sure that we normalized u when we put it together. We also talked about the largest and greatest value of our directional derivative, which would be equal to del f, and I will get to an example involving that. Then we also talked about optimization in multivariable calculus, so the idea of critical points. Because now we are dealing with more than one variable, we have to make sure that f of x equals 0 or does not exist, and f sub y equals 0 as well, or does not exist. So as long as our x and y variables satisfy both partials equal to 0, then it is a critical point. And then what we looked at was this determinant matrix, which involved our second derivatives. And this determinant matrix basically decided if we had a relative max or minimum. So if d was greater than 0, we were looking at an extrema. And what we looked at was, for example, f sub xx. If that was greater than 0, then it was concave up, and you had a relative minimum. If f sub xx was negative, then it was concave down, and you had a relative maximum. If the determinant matrix was less than 0, then you had a saddle. And if it was equal to 0, it was inconclusive. We talked about how it meant differently now if we had to deal with absolute extrema, and then we had something called the Lagrange Multipliers. And that was basically looking at the gradients again and saying that at an optimum value, our normals would have to be parallel to each other. So I'll get to each of those examples. We're going to start with our directional derivative. So let's just start with a straight up directional derivative problem. We have a function here, sine y plus e to the xy. I'm going to find the rate of change at a specific point in a particular direction. So the directional derivative of f in the direction of u is equal to del f dot u over its magnitude. Del f is my partial with respect to x, which is y e to the xy. And my partial with respect to y, which is cosine y plus x e to the xy. Evaluated at a particular point, 1 comma pi, this is going to equal pi e to the pi, negative 1 plus e to the pi, dot my vector u, 2 comma 4, all over its magnitude, 20. So multiplying this out, my directional derivative is going to be 2 square root of 20 pi e to the pi plus 4 over the square root of 20 e to the pi minus 1. Now we also talked about how the directional derivative could equal del f dot cosine theta sine theta. Where theta represented the angle of interest, but notice that I have those two values here and here, and it's divided by the root. So in this case, cosine theta was 2 over square root of 20, and sine theta is 4 square root of 20. So it's analogous. Alright, if I want to find the direction and the value of greatest increase and decrease, we talked about how that was related to the gradient in class. So del f the magnitude of del F is the greatest increase and it's in the direction of del F. So in our particular case here, the greatest increase or the largest slope would be equal to the magnitude of pi e to the pi squared plus e to the pi minus 1 squared. And it is in the direction of del F, which is pi e to the pi minus 1. Similarly, our greatest decrease or our most negative slope would be in the direction of negative del F and has magnitude equal to the negative magnitude of del F. So in this case, our greatest decrease would be equal to negative pi e to the pi 1 minus e to the pi, and the magnitude, or the value of that most negative slope, would be negative the square root of negative pi e to the pi squared, or actually just e to the pi squared, plus e to the pi minus 1 squared. So that would be negative del F. Yes. Alright, let's take a look at a temperature problem. So the idea here is I have an object that's going to follow the path of greatest temperature change. Now the greatest temperature change is represented, this one here, is represented by del F. So that's going to equal x squared plus 1 e to the y and negative 8c. The position of the object is represented by r of t. But since I'm interested in the motion of the object, we're going to look at r prime of t. So that's going to equal dx dt, dy dt, and dz dt. Now, I want these two directions to be going the same way, but they don't exactly have to be equal to each other. So then del F has to equal a multiple of r prime of t. So that means that x squared plus 1 e to the y negative 8c has to equal some multiple of dx dt, dy dt, and dz dt. So if I set these components equal to each other, I get x squared plus 1 equals k times dx dt. I get e to the y equals k times dy dt. And I get negative 8z equals k times dz dt. So technically what we're looking at here are three differential equations. If I separate the variables, I get 1 over k dt equals dx over x squared plus 1. Integrating both sides, I'm going to get arc tangent of x equals to 1 over kt, or let's say, t over k plus c. And I have initial condition, so I know since it's at the point 1 to negative 5, when t equals 0, that means x equals 1, so c equals pi over 4, and so I have arc tangent of x equals t over k plus pi over 4, or x equals the tangent of t over k plus pi over 4. Doing the same thing with the others. If I solve here, I get e to the negative y gy equals 1 over k dt. And integrating this out, negative e, whoops, negative e to the negative y equals 1 over kt plus c. When t equals 0, y equals 2. So then the second half equation comes out to be equal to y equals negative natural log e to the negative 2 minus t over k. And then the last one, if I solve this one out, I get dz over z equals, let's see, d over z, so negative 8 over k dt. Integrating both sides, ln of z equals negative 8 over kt plus c. So z equals ae to the negative 8 over kt. Putting in my initial condition, t equals 0, z equals negative 5. That means my equation is z equals negative 5 e to the negative 8 over kt. Now, if you notice, all of these have the same parameter. They all have a t over k. So t over k here, and here, and here. So what I'm going to do is I'm going to reparameterize that into a new t defined by t over k, and I can write three parametric equations then for x, y, and z. So x equals the tangent of t plus power 4. Y equals the negative natural log of e to the negative 2 minus t? I think so. And z equals negative 5 e to the negative 8. So technically you don't need that k in there, but I wanted to show you theoretically that the k should be in there, but then later on when you reparameterize it, you don't need the k to reparameterize it as a result. Yes. Okay, so that's the answer to that one. Okay, let's see what else we can do with the gradient here. Oops. So, from the top, find the equation of a plane. So remember, the gradient is normal to my tangent vector for a specific level surface. And what we have to do first is rewrite this as a level surface. So I'm going to rewrite this as the natural log of 3x plus 7y minus z equals 0. And then we're going to find the gradient. So del f is going to equal 3 over 3x plus 7y 7 over 3x plus 7y, and negative 1. So if I substitute in my point, I get negative 6 plus 7. So it's 3, 7, and negative 1. My point, f of negative 2, comma 1, is equal to the natural log of 1, which is 0. So my point for my plane is negative 2, 1, 0. And then don't forget, this is basically my normal vector. So the equation of the plane is going to be 3 times x plus 2 plus 7 times y minus 1 minus 1 times z minus 0 equals 0. And that should technically look very familiar from what we did in the earlier part of chapter 12. If you recall from the earlier part of chapter 12, we had the equation of the plane z minus z naught equals the partial with respect to x minus x naught, plus the partial of with respect to y times y minus y naught, which you see in that equation that I just wrote. Now, if I want to find the equation of a normal line, I actually have all the information here, because for a normal line, I need a vector, which is going to be my 3, 7, negative 1, and my point, which is going to be negative 2, 1, 0. So negative 2, 1, 0 is my point. 3, 7, negative 1 is my direction. So my line is going to be x equals negative 2 plus 3t, y equals 1 plus 7t, and z equals 0 minus 1t. Now, angle of inclination, what we did was we thought of it in terms of the normal vector and thought of how the normal vector could help us out. So if I were to draw a schematic here, now it's with respect to the YZ plane. So for our sake visualization, let's pretend that's the YZ plane. I have a plane that's going through here at some angle, and the angle of inclination with respect to the YZ plane is this angle right here. So I could find a vector on my plane, and then find another vector on the YZ plane, and then do the arc cosine of that. But since we were talking about gradients, we could also think of it the following way. Since the gradient is the normal vector, this is my del f, I could talk about the angle between the gradient vector and the x-axis, which would be 0, 0, 1. So cosine theta would equal my gradient vector dot my x-axis, which I'll call 1, 0, 0, over the magnitude of my gradient vector and the magnitude of my x-axis, 1, 0, 0. So del f is 3, 7, negative 1, dot my x-axis, all over the square root of 9 plus 49 plus 1. So theta equals the arc cosine of 3 over the square root of 59. And then the last one I want to do with this example is the idea of two intersections. So the way we kind of tried to visualize this is, let's say I have two level surfaces. And then basically what I want to do is I want to look at the normals of each of these level surfaces. So for example, let's say I have a tangent plane here, and my normal vector is going one way. So let's call this del f. And then I have my tangent plane, and my normal vector is going the other way. So let's call this del g. Then del f del cross del g is going to be something perpendicular to both of them at the same time, and it's going to go something like this. And that's going to be my line, tangent line, to the intersection of the two curves. So del f, we already had from before. Del f was equal to 3, 7, negative 1. So now I'll need del g. Now technically, again, I got to rewrite this into a level surface. So x squared minus y squared minus z equals 3. Let's say that's my level surface. Then my del g equals 2x, negative 2y, and negative 1. So at my point of interest, that's going to be negative 4, negative 2, negative 1. So del f cross del g, del f cross del g, is going to equal negative 7 minus 2, which is negative 9, negative 3 minus 4, which is negative 7, so positive 7, negative 6 plus 28, which is 22. So there's my direction, here's my point. So my equation would be x equals negative 2 minus 9t, y equals 1 plus 7t, and z equals 0 plus 22t. Alright, we're going to do some optimization next. So, relative extrema means I'm going to set my partials equal to 0 to find the critical points, which have to set make both partials equal to 0 as a result. So, f of x would equal 4x cubed minus 4y, and that has to equal 0. F sub y equals 4y cubed minus 4x, and that has to equal 0 as well. So if I take the first equation, I get y equals x cubed. If I substitute that into my second equation, 4y cubed minus 4x equals 0. Let's get rid of the 4's. Then I would have x to the 9th minus x equals 0, which factors into x to the 4th plus 1, x to the 4th minus 1, which factors into x squared plus 1, and x squared minus 1. So my critical points would be x equals 0, 1, and negative 1. And likewise, y would equal 0, 1, and negative 1. So my critical points are 0, 0, 1, 1, and negative 1, negative 1. Now let's see what we get if we solve in the other direction. So if I take this equation, I get x equals y cubed. And if I substitute into the first one, I get 4y to the 9th minus 4y equals 0. I'm going to cancel out the 4's again. That factors into y to the 4th plus 1, y squared plus 1, y squared minus 1 equals 0. So y equals 0, 1, and negative 1, which I took care of already in the first one. So I have all the critical points. Now I need to determine if these critical points are relative max or relative min. So I'm going to take a look at my second partial derivative, which would be f of x, xx, which is 12x squared, fxy, which is negative 4, fyx, which is negative 4, and fyy, which is 12y squared. I'm going to look at each of these points. So for example, at 0, 0, if I substitute that in, I get 0, negative 4, negative 4, 0, which equals negative 16. That's less than 0. So I have a saddle at x equals 0, y equals 0, and then substituting all the way into the original equation, that's at a z-coordinate of 1. If I take 1 comma 1, I get 12, negative 4, negative 4, 12. So that equals 144 minus 16, which is greater than 0. Looking at the first component, fxx is greater than 0, so it's concave up. And so I have a relative minimum at 1, 1, negative 1. And then likewise, negative 1, negative 1. I have 12, negative 4, and 12, which we already figured out is greater than 0. This indicates that it's still concave up. So I have another relative minimum at negative 1, and that z value is also negative 1. I hope. 1, 2, negative 2, negative 1. Yes. Okay, so that takes care of that. Now, that's all the relative extrema. So now I want to look at the absolute extrema over a particular region. Unfortunately, I picked a fairly easy region, but hopefully it gets your point across. So we're looking at this region here between y equals x and y equals x squared minus 2. And technically what we have is we have two edges. And so I need to figure out if there's an absolute extrema on either of the edges. So let's start with our first one. Our first edge is when y equals x, and I only want to use that between the 2 points of intersection, so between negative 1 and 2. So what I want to do in my original function of f of xy is everywhere there's a y, I'm going to substitute it with an x. So now this becomes f of x comma x equals x to the 4th plus x to the 4th minus 4x squared plus 4. Now, I put this in my calculator and solved it out. I was looking for the absolute max and absolute mins along this edge. So I believe the maximum was at x equals 2. So when x equals 2, y equals 2, and the function value is equal to 17. And then the minimum actually occurred in two places because I have this 4th degree polynomial. The minimum occurred at 1 and 1, which was negative 1, and at negative 1, negative 1, negative 1. So that's my first edge. Now let's take a look at the other edge. So the other edge would be y equals x squared minus 2. So same thing, everywhere there's a y, I'm going to replace it with x squared minus 2. And again, my bounds are between negative 1 and 2. So now my function becomes f of x, x squared minus 2, equals x to the 4th plus x squared minus 2 to the fourth minus 4x x squared minus 2 plus 1. And again, what I did was I graphed it to find the minimum and maximum values. I actually found two maximum values this time, if I did this correctly. One at 0, negative 2, 17, and also at 2, 2, 17. And then I found the minimum at negative 1, negative 1, negative 1. So if I compare all these values and the relative extrema, it looks like my absolute max for the function is 17, and my absolute minimum for the function is negative 1. Now I wanted to do a circle region because some people had some questions about this. But let's go through from the very beginning. So let's start with our relative. So f of x equals 0 would mean that y squared equals 0. Well, that's good. So that means y equals 0. If I set my partial with respect to y equal to 0, I get 2xy equals 0. But y already equals 0, so what that means is x is actually any real number. So I have a critical point, or I guess critical points, along the line x comma 0. Now, if I do my partials, my second derivatives, d is going to equal 0, 2y, 2x, and 2x. But notice, regardless of what values of x or y I put in, this is going to equal 0, which is where it was inconclusive. So now we got to think of it graphically. Well, I know y squared is going to always be positive, but x can be positive or negative. So what that actually means is along these critical points, I have a saddle. And so what I did was I graphed it. And you can kind of see the saddle there as a result. So everything in the middle along x equals y is a saddle. That means we're going to take a look at our ends instead. So this time, because we're graphing over x squared plus y squared equals 4, and that graphs a circle, I'm actually going to just treat that as one edge. And the edge would be where x squared plus y squared equals 4. But since it's a circle, I'm going to convert it to polar. And I'm going to think of this as r equals 2 instead. So then that would mean that x equals 2 cosine theta and y equals 2 sine theta. And my function, f of xy, is now going to become f of theta, and it's going to equal 8 cosine theta sine squared theta. So I graphed this and found the maximum minimums. The maximum was at theta equals 0.955 and also at theta equals 5.327. So using my definition for x and y here, I found the corresponding points. That was 1.153, 1.633, and then the function value was 3.079. It also occurred at 1.153, negative 1.633, and again the same max value, 3.079. My minimums occurred at theta equals 2.186 and 4.097, and the corresponding x and y values were negative 1.153, 1.633, negative 3.079, and negative 1.153, negative 1.633, and negative 3.079. Alright, let's do some optimization problems. So, shortest distance from a point to a plane. We're trying to optimize distance here. So, our distance equation would be d squared equals x minus 1 squared plus y squared plus z plus 2 squared. I have this constraint, so I'm going to use that to reduce my 3 variables down to 2 variables. So I solve for x equals 4 minus 2y minus z, and substitute that in. So this becomes, let's see, that'll become 3 minus 2y minus z squared plus y squared plus z plus 2 squared. And so now I want to take the partials with respect to y and with respect to z and set them each equal to 0. So d squared's partial with respect to y is going to be 3 minus 2y minus z, and then chain rule, so times negative 2 plus 2y equals 0. I'm going to cancel out those 2's. And then my partial with respect to z is going to be 3 minus 2y minus z times negative 1 plus 2 times z plus 2. Same thing, I'm going to cancel those out. So if I simplify this, I'm going to have, let's see, negative 6, 4y plus y, so plus 5y plus 2z equals 0. And then in the other one, I'm going to have negative 3 plus 2y, negative 1, negative 1, plus 2y, plus z, plus 2z equals 0. So if I subtract these two, I get negative 5 plus 3y equals 0, and y equals 5/3. And then if I know y, I can go back and solve for z. Z equals negative 7/6. And if I know y and z, I can solve for x, and x equals 11/6. Now, that was using the partials, but we also learned the Lagrange multiplier idea, so I wanted to use that as well. For the Lagrange multiplier, we're trying to optimize our distance, so d squared equals x minus 1 squared plus y squared plus z plus 2 squared. And then we have our constraint, x plus 2y plus z equals 4. So what we're going to do is find the gradient for each of these. Del d squared would equal 2x minus 1. It would equal 2y and 2z plus 2. And then let's call this one del g for the constraint, which would be 1, 2, 1. So the Lagrange multiplier idea says that del d squared is some multiple of del g. So that means that 2x minus 2, 2y, 2z plus 4, that's a 4, has to equal lambda times 1, 2, 1. So if I break this up into components, that means 2x minus 2 has to equal lambda. That means 2y has to equal 2 lambda. And that means that 2z plus 4 has to equal lambda. So what I want to do is actually solve for x, y, and z in each one of these. So this one here, I'm going to get x equals lambda over 2 plus 1. For the next one, I'm going to get y equals lambda. And then for the last one, I'm going to get z equals lambda over 2 minus 2. Because what I can do is I can put this in the constraint that x plus 2y plus z equals 4 and solve for lambda. So I'm going to get lambda over 2 plus 1 plus 2 lambda plus lambda over 2 minus 2 equals 4. Let's see, so that's going to be 3 lambda equals 5, lambda equals 5/3, which checked out. So that means y equals 5/3, which proves with my previous problem. That means x equals 5/6 plus 1, which is 11/6, which equals with my other attempt. And z equals 5/6 minus 12/6, which is negative 7/6, which also agrees with my other attempt. So, how to choose what to do with each one of these? Well, let's say I was given this problem. A rectangular box is to be made from 12 square meters of cardboard. Find the maximum volume. So we're going to assume all 12 meters squared of the cardboard is actually going to get used for this. We're trying to maximize the volume. So volume equals xyz. Our constraint is that 2xz plus 2yz plus 2xy equals 12. So then we get xz plus yz plus xy equals 6. So I'm going to actually show both ways again for this, just so you see the difference between the two. So let's say I start, oops, that's a 6. Let's say I start by solving for x. So x is going to equal 6 minus yz all over y plus z. So if I substitute that in, I get v equals, let's multiply this out. So that'll be 6yz minus y squared z squared all over y plus z squared. So my partial with respect to y would be bottom times the derivative of the top, which would be equal to 6z minus 2yz squared minus the top, ooh, there's no square, minus the top, which would be 6yz minus y squared z squared times the derivative of the bottom, which is 1. So that works out nicely. Okay, and then all over the bottom square. Now, I think when this simplifies out, you get negative z squared y squared plus 2yz minus 6 all over y plus z squared. Now let's do the same for v sub z. So v sub z would be bottom function times the derivative of the top minus the top function derivative of the bottom, which is 1, all over bottom squared. So multiplying this one simplifies out to negative y squared, z squared plus 2zy minus 6 all over y plus z squared. Now each of these has to equal 0. So let's look at the first case. If I look at v sub y equal to 0, what that would mean is z equals 0 or y squared plus 2yz minus 6 equals 0. Now if I take z equals 0 and put it into my second equation though, if I put that into v sub z, I get 6y squared over y squared equals 0, but 6 doesn't equal 0, so that means that's no solution. So it means it has to be this one over here. And similarly, v sub z equal to 0, I'm going to get the same thing. So my only alternative is that z squared plus 2yz minus 6 equals 0. And if I subtract these, what I get is y squared minus z squared equals 0. So y equals plus or minus z. Substituting that into the equation, I get 3y squared minus 6 equals 0. So y equals plus or minus root 2, and then z is each of the components. So my critical points would be root 2, negative root 2, negative root 2, root 2, negative root 2, and negative root 2, and root 2. And then I'd have to do a second derivative, which is really ugly. So let's use our Lagrange multipliers instead. Okay, so to recap, I'm optimizing volume, v equals x, y, z. I have the constraint, xz plus xy plus yz equals 6. So if v equals, how about? So if I set up my normals for these, del v would equal yz, xz, and xy. And let's call this g. Del g would equal z plus y, x plus z, and x plus y. And since del v has to equal lambda del g, then that means that yz, xz, and xy has to equal lambda z plus y, x plus z, and x plus y. So yz has to equal lambda z plus y, xz has to equal lambda x plus z, and xy has to equal lambda x plus y. Now, if you recall my trick in class, what I suggested was multiplying the first one by x, the second one by y, and the third one by z, because then you get x, y, z equals lambda x, z plus y. You get x, y, z equals lambda y, x plus z. And you get x, y, z equals lambda z, x plus y. So since they're all equal to x, y, z, I can actually set them equal to each other. So for example, if I set these two equal to each other, lambda x, z plus lambda x, y equals lambda y, x plus lambda y, z. Those cancel. Lambda can't equal 0, so I can cross those out. And we get x equals y. And then similarly from these, we get y equals z. So if I use all that and this constraint here, I'm going to have 3x squared equals 6, x equals plus or minus root 2. So my critical points would be root 2, root 2, root 2, which would give me my largest volume. And if this wasn't a volume equation, I just wanted you to find the maximum minimum value of v, quote unquote, then negative root 2, negative root 2, negative root 2 would be my minimum value of v, which would be negative 2 root 2. Lastly, I want to set up a Lagrange with two constraints. So the idea here is that I'm trying to optimize something, but I have two conditions that are kind of holding me back. So Lagrange says that if you have two constraints, then del f has to equal a linear combination of the other two constraints. So I would call it lambda 1 del g1 plus lambda 2 del g2. So let's call this one here g1, and this one here g2. Now again, with g1, I got to rewrite as a level surface. So I'll write this as x squared minus 2xy plus 3y minus z. And g2 is already good. So del f would equal 2x, 3z, 3y equal to lambda 1. G1 would be 2x minus 2y, negative 2x plus 3, and negative 1. And del G2 would equal 1, 8y, and minus 3. So, matching up my three components, I would have 2x equals lambda 1, 2x minus 2y, plus lambda 2. I would have 3z equals lambda 1, negative 2x plus 3, plus lambda 2 times 8y. And I would have 3y equals lambda 1 times negative 1 plus lambda 2 times negative 3. So I think if it were up to me to solve, looks like here I could solve for y in terms of lambda 1 and lambda 2, substitute it in, and generate 4 equations with 4 variables, and just kind of keep substituting like that. Now keep in mind I have these 3 constraints, or these 3 equations to help solve for x, y, and z, and I also have my original equations here and here to solve for x, y, z, lambda 1, and lambda 2, whatever is necessary as a result. Okay, so that's the setup for Lagrange with 2 constraints. We will practice on Monday and do some review this week as well and get you ready for the test. Good luck studying, everyone.